Bismillahirrahmanirrahim. Today's lecture outline is electric potential, potential difference, electric potential energy, potential due to point charge, equipotential lines, equipotential surface, potential gradient, and electron volt. Our first topic, which is electric potential. According to the definition, the amount of work needed to move a unit charge from a reference point to a specific point inside the field is called electric potential. It means that if we would like to move a charge from one point to another point or reference point to a specific point, then how much work done on that charge is known as electric potential. The formula for the electric potential is V is equals to W over Q, and it is denoted by V, capital V, or its unit is joule per coulomb, and this V is known as volts, or we can measure the electric potential in volts. Now move towards another topic, which is potential difference. It means that it is also same as electric potential, or we can say that the difference between two electric potentials is known as potential difference. We have in any circuit or in any electrical charges or distribution of electric charges, we know that positive charges are high potential and negative charges are low potential, and the difference between these potentials is known as potential difference. But for our convenience, we drive or we write an appropriate definition for this potential difference, which is same like as the definition of electric potential, and this is the amount of work done in moving a unit charge from one point to another point, keeping the charge in electrostatic equilibrium inside the field is called potential difference. It means that uh, if we would like to move a charge from one point to another point, but the important thing is that the movement of charge will be in electrostatic equilibrium inside any field. यानी कि हम कह सकते हैं कि चार्ज जब मूव कर रहा हो तो वो इलेक्ट्रोस्टैटिक इक्विलिब्रियम को डिस्टर्ब ना करे, बल्कि इलेक्ट्रोस्टैटिक इक्विलिब्रियम को मेंटेन रखते हुए उसी फील्ड के अंदर मूव कर रहा हो, तो इस कंडीशन में उसमें जो वर्क डन की अमाउंट हमें रिक्वायर्ड होगी वो पोटेंशियल डिफरेंस कहलाएगी. It is also represented by delta V, and delta V is equals to work done per unit charge, or W upon Q. Next topic, which is electric potential energy. Consider an isolated point charge Q fixed in space. If a test charge Q is placed at infinity, the force on it due to charge Q is 0. We know that if a charge is at infinite distance, we can say that it is from outside from the electric field, so the electric field intensity or the electric potential energy will be zero, at the infinite point, because the charge test charge Q is beyond the electric field. Now here we have a diagram. We have a positive charge and a charge Q, which is a test charge Q, which is at infinite distance from that positive charge Q, capital Q. Now we wish like to bring this charge inside this electric field of positive charge, and for this we do a work on that charge Q and move that charge Q from infinite point to point A. When it becomes to point A, it experiences a force on it because it will become inside the electric field, and from A to B we divide all the distance from A to B in a small path which is known as delta R. Delta R1, R2, R3, R4 up to Rn, and then the point Rb where we have to calculate the electric potential energy. As the test charge is at infinity, so work is required to be done to bring it to point A. Hence, when the test charge is at potential A, it has some amount of electric potential energy, because if it inside the electric field, then it has some amount of electric potential energy, and it will experience a Coulomb force at that point or at the point A, because it will inside the electric field. Now electric field does not remain constant, because the charge move inside the electric field. Now the electric field vary point to point on that charge. In order to keep E constant, the test charge is moved through infinitesimally small displacement delta R. If we wish like, or if we would like to make E constant, then we divide these all this all displacement from A to B in small patches, which is 1, 2, 3, 4, 5 and up to n term. Now the work done can be calculated as, if we do work done on that charge, so we can calculate that work in the from the formula delta W is equals to F dot delta R, and F delta R cos 180 degree. Why we put 180 degree? Because we move that test charge towards positive charge, and we move this test charge against the electric field, because the Coulomb force show that a repulsive force between these two charges, because they are same in polarity. Or we can say that the electric field outward from positive charge, and we move that positive test charge inside the electric field or towards the charge. So we can say that we move this q uh, we move this q opposite to the electric field. F and R in opposite direction. So delta W become F delta R minus 1 cos 180 degree equals to minus 1, and the work done will be delta W is equals to minus F delta R. Now if we put the value of A due to the from the electric field intensity or electric field, we get delta W is equals to minus EQ delta R, which is equals to EQ delta R. We put negative sign with electric field, because electric field is outside from positive charge, and charge move inside or towards that positive charge. That's why we use negative sign, and negative will be positive. So the result will be EQ delta R with positive sign, and this will your equation 1. By putting the value of E in equation 1, we get delta W is equals to 1 upon 4 pi epsilon naught Q upon R square Q delta R. The value of E we have derived in previous lecture. So the value of E put in equation 1, and we get the result delta W is equals to 1 upon 4 pi epsilon naught Q upon R square delta R. Now let the test charge is at a distance Ra from charge Q. We know that the test charge is at point A, and the distance between Q and A will be Ra. We divide the distance between Ra and Rb. Ra and Rb के distance को हम divide करेंगे into n number of small equal displacement, because we have to maintain E, because we know that E vary from point to point. So we to make an equilibrium state, or to make an equilibrium in electrostatic state, we divide this whole path into small distances, which is known as delta R. Now the amount of work done from point A to 1 can be calculated as delta W A to 1 is equals to 1 upon 4 pi epsilon naught Q upon R square delta R. Here it is not A minus 1, it is A to 1. It means that from point A to point 1, we move charge from point A to point 1, and the work done on that charge will be 1 upon 4 pi epsilon naught capital Q small q divided by R square delta R. This will be equation 2. Now we have to calculate R square. For this, we note the average distance between R1 and RA, which is R1 plus RA upon 2, and we know that delta R is RA minus R1. Now RA equals to delta R plus R1. We move our negative R1 towards delta R, then negative become positive. By putting the value of RA in above equation, we get R is equals to R1 plus delta R plus R1 upon 2. The value will R is equals to R2R1 plus delta R upon 2, because R1 and R1 will become 2R1. We separate these values. R is equals to 2R1 upon 2 plus delta R upon 2. 2 will be cancelled by 2, and the remaining value will be R is equals to R1 plus delta R upon 2. By squaring above equation R square, and we put the formula A plus B whole square on above equation, so we get R1 square plus 2R1 delta R upon 2 plus delta R upon 2 R square whole square. 2 will be cancelled by 2, and the remaining value will be R square is equals to R1 square plus R1 delta R. Here delta R is much smaller than the distance between RA and RB, so we neglect this term, because by squaring delta R upon 2 it becomes more smaller, so we neglect this term, and the result will be R square is equals to R1 square plus R1 delta R, and R square equals to R1 square plus R1, and by putting the value of delta R, which is RA minus R1, we get R square is equals to R1 square plus R1 RA minus R1 square. We cancel R1 square with R1 square, and the result will be R square is equals to R1 RA. By putting all the values in equation 2, we get delta W A to 1 is equals to 1 upon 4 pi epsilon naught capital Q small q divided by R1 RA multiplied by RA minus R1. Now we can write this equation: delta W is equals to Q upon 4 pi epsilon naught RA minus R1 upon R1 RA. By separate this equation, delta W is equals to Q upon 4 pi epsilon naught RA upon R1 RA minus R1 upon R1 RA. RA will cancel by RA, and R1 will cancel by R1. So we get delta W A to 1 is equals to Q upon 4 pi epsilon naught 1 upon R1 minus 1 upon RA. The amount of work done from point 1 to 2 can be calculated as delta W 1 to 2 1 upon 4 pi epsilon naught Q upon R square delta R, and 1 upon 4 pi epsilon naught Q upon R1 R2 by putting the value of R square here, and delta R will become R1 minus R2. Similarly, we write this equation Q upon 4 pi epsilon naught R1 minus R2 divided by R1 R2. Delta W is equals to QQ upon 4 pi epsilon naught R1 upon R1 R2 minus R2 upon R1 R2. R1 will cancel by R1 and R2 will cancel by R2, and the result will be delta W is equals to QQ upon 4 pi epsilon naught 1 upon R1 minus 1 upon R2 minus 1 upon R1. Now the amount of work done from N to B can be calculated as W N to B is equals to 1 over 4 pi epsilon naught capital Q small q upon R square delta R, where we put value of R square and delta R. So we get delta W N to B is equals to 1 upon 4 pi epsilon naught QQ upon Rn RB Rn minus RB, and delta W up N to B is equals to Q upon 4 pi epsilon naught Rn minus Rb over Rn Rb. Now separate these equations, so we get delta W N to B is equals to Q small q upon 4 pi epsilon naught Rn over Rn Rb minus Rb over Rn Rb. Now Rn cancel with Rn and Rb cancel with Rb, so we get delta W N to B is equals to QQ upon 4 pi epsilon naught 1 over Rb minus 1 over Rn. Thus, the total work done in moving a charge Q from A to B can be calculated as, now we summarize or we make a sum of all individual work done from A point to point B, in which we have small pitches 1, 2, 3, 4 up to N from. So we get delta W A to B is equals to delta W A to 1 plus delta W 1 to 2 plus delta W 2 to 3 and so on to delta W N to B. By putting the value, delta W is equals to Q upon 4 pi epsilon naught 1 over R1 minus 1 over RA plus QQ upon 4 pi epsilon naught 1 over R2 minus 1 over R1 plus so on to QQ upon 4 pi epsilon naught 1 over RB minus 1 over Rn. Now delta W is equals to QQ 4 pi epsilon naught 1 over R1 minus 1 over RA plus 1 over R2 minus 1 over R1 plus up to 1 over RB minus 1 over Rn. Uh, uh, Here we take common QQ over 4 pi epsilon naught, which are same in all terms, and the remaining terms we write in bracket. Now delta W A to B is equals to QQ upon 4 pi epsilon naught minus 1 over RA plus 1 over RB. यहाँ आपके पास तमाम 1 over R1, 1 over R2, 1 over R3, 1 over R4 ये तमाम के तमाम नेगेटिव और पॉजिटिव वैल्यू एक दूसरे के को कैंसिल कर देंगी, और सिर्फ रिमेनिंग वैल्यू जो हमारे पास रहेगी वो रहेगी 1 माइनस 1 ओवर RA प्लस 1 ओवर RB. इसको जब रीअरेंज कर लेंगे, so delta W A to B is equals to QQ upon 4 pi epsilon naught 1 over RB, क्योंकि पॉजिटिव का है इसको पहले लिख लिया, minus 1 over RA. The work done to move a test charge Q from infinity to point B can be calculated as, now we have to calculate the total work done from point infinity to point B, यानी कि उस पॉइंट से जहां चार्ज सबसे पहले मौजूद था और उस पॉइंट तक जहां पे हमें इस चार्ज को लेके आना है, वहां तक जब वर्क डन कैलकुलेट करते हैं तो वी नो दैट delta W A to B is equals to QQ upon 4 pi epsilon naught 1 over RB minus 1 over infinity, because RA is a point of infinity. So delta W A to B is equals to QQ upon 4 pi epsilon naught 1 over RB, because we know that 1 over infinity equals to 0. So the negative term of this above equation becomes 0, and the remaining term will be delta W A to B is equals to QQ upon 4 pi epsilon naught 1 over RB के बराबर आ जाएगी. Now the electric potential energy at distance R from Q is, now distance एक finite distance R से लेके R तक की potential energy, electric potential energy from charge Q will be delta W is equals to QQ 1 over 4 pi epsilon naught 1 over R के बराबर आ जाएगी, क्योंकि B point, we have B point as a reference point, or we consider this point. So the main point is that there is a distance from charge Q to charge small q, and this distance is denoted by R. तो उस R को हमने यहाँ पे लिखा और हमारे पास जो वैल्यू आ गई वो आपके सामने है. This is the expression to find electric potential energy. ये expression आपके पास electric potential energy की expression है. Now we move towards electric potential due to a point charge. Now what is the value of electric potential? Because the above equation is the value of electric potential energy, not only electric potential. We have to calculate electric potential due to point charge. So for this, electric potential at distance R from Q is, we know that potential equals to work done per unit charge. Put the value of work done in this above in this equation. V is equals to Q upon 4 pi epsilon naught 1 over R over Q. Q cancel small q, and we get V is equals to 1 upon 4 pi epsilon naught Q upon small r. The above equation is used to calculate the electric potential due to point charge. Now move towards today's another topic, which is equipotential lines. The word equipotential comes from two words or combination of two words. One is equal and other is potential. Equipotential. It means that a point or a line where we have same amount of potential by a charge is known as equipotential lines. The imaginary lines at which electric potential is same at every point is called equipotential lines. यानी कि वो lines जहां पर आपके पास इलेक्ट्रिक पोटेंशियल की वैल्यू सेम हो, या वो इमेजिनरी लाइन जो उन तमाम पॉइंट्स से होकर गुजरती हो जहां पर इलेक्ट्रिक पोटेंशियल की वैल्यू सेम हो, इस लाइन को हम इक्विपोटेंशियल लाइन का नाम देते हैं. एन इक्विपोटेंशियल लाइन connects point in space where the potential of an electric field is same. वही बात कर दी यहाँ पर कि आपके पास उन तमाम पॉइंट्स को ज्वाइन करने वाली लाइन जिन पॉइंट्स के ऊपर पोटेंशियल की वैल्यू सेम है. Equipotential lines are always drawn perpendicular to the electric field. In electric field, क्योंकि हमें पता है हम इलेक्ट्रिक फील्ड की जब वैल्यू बनाते हैं या इलेक्ट्रिक फील्ड की डायग्राम जब हम बनाते हैं तो उस इलेक्ट्रिक फील्ड की डायग्राम को हम शो करते हैं द लाइंस इमिट आउट फ्रॉम अ पॉजिटिव चार्जेस और एंटर्स इन अ नेगेटिव चार्ज. इन लाइंस या इन इमेजिनरी सरफेसेस के परपेंडिकुलर मौजूद लाइन को हम इक्विपोटेंशियल लाइन का नाम देते हैं, या हम ये कह सकते हैं कि इक्विपोटेंशियल लाइन इस इलेक्ट्रिक फील्ड की लाइन को परपेंडिकुलरली क्रॉस कर रही होती है, जैसा कि इस डायग्राम में आपको दिखाया जा रहा है. A positive charge whose electric field is in the circular path of the charge or around the charge Q, and the equipotential lines are these lines which are perpendicular to that concentric circles. Now, if there are two or more charges present, then the equipotential at any point is the sum of potential due to these charges or due to each charge. If we have two charges, दो चार्जेस आपके पास मौजूद हैं, तो आपके पास इक्विपोटेंशियल लाइंस जो होंगी वो बेसिकली इन दोनों चार्जेस की इक्विपोटेंशियल लाइंस का सम होंगी. यानी कि हम तमाम इक्विपोटेंशियल लाइंस को ऐड करेंगे और जो पोटेंशियल आपके पास इस वक्त आएगा उस पोटेंशियल को हम वहां पर टोटल इक्विपोटेंशियल लाइंस का नाम देंगे. नाउ इक्विपोटेंशियल सरफेस, if you clear about equipotential line, then you don't have any doubt in equipotential surface. It is a surface where the potential are same, और हम कह सकते हैं कि ऐसी सरफेस, ऐसे रीजन को हम इक्विपोटेंशियल सरफेस का नाम दे सकते हैं जहां पर आपके पास तमाम का तमाम पोटेंशियल उस पूरे सरफेस पे एक जैसा हो. द सरफेस वेयर इलेक्ट्रिक पोटेंशियल इज सेम at every point is called equipotential surface. Now moving towards another topic, which is potential gradient. Potential, we know about the concept of potential, and what is gradient? Gradient means that change. Potential का change किस हिसाब से चेंज आ रहा है उस चीज को हम देखेंगे इस टॉपिक के अंदर, और वो आपके पास है relation between electric intensity and electric potential. The rate of change of electric potential with respect to displacement is known as potential gradient. Here we can say that the change in electric potential due to the change in displacement or due to the displacement is known as potential gradient. Suppose that consider two parallel charge plates A and B. They are separated by distance delta r. If a test charge Q naught is placed between the plate, then an electrostatic force EQ naught applied on it, which moves the charge downward towards negative plate B. Here there are two plates, one is A and second one is B. The A is positively charged plate and B is negatively charged plate. We know that the behavior of electric field always from high potential to lower potential, or we can say that from positive plate to negative plate. Here we insert, and the distance between these plates are delta r. Here we insert a test charge Q naught, and on this test charge an electrostatic force applied as a repulsive force, because test charge have a polarity of positive, and positive plate means plate A. Plate A apply a force on that charge and move this charge towards plate B. यहाँ पर ये जो चार्ज है आपके पास, ये चार्ज हमने इन दोनों प्लेट्स के दरमियान जैसे ही इंसर्ट किया तो पॉजिटिव प्लेट इस चार्ज पर एक फोर्स अप्लाई करना शुरू कर देगी और ये चार्ज डाउनवर्ड मूव करना शुरू कर देगा. अब इस चार्ज को इक्विलिब्रियम स्टेट पे रखने के लिए हम एक एक्सटर्नल फोर्स, एक एक्सटर्नल इलेक्ट्रिक फोर्स इस चार्ज पे अप्लाई करते हैं, जो कि अगेंस्ट होगी उस इलेक्ट्रिक फील्ड के बिहेवियर के जो यहाँ पर आपके पास फ्रॉम पॉजिटिव टू नेगेटिव प्लेट शो किया गया है. तो यहाँ पर हम जब चार्ज के ऊपर फोर्स अप्लाई करेंगे तो ये फोर्स आपके पास अपोजिट इन डायरेक्शन होगी फ्रॉम दैट फोर्स विच इज अप्लाइड बाय पॉजिटिव प्लेट on the charge Q naught, and this force is opposite in the direction of electric field. An external force F is required to maintain electrostatic equilibrium. If we apply a force on that charge, then charge becomes in electrostatic equilibrium, or we can say that we do a work on that test charge, and the work done will be against the electric field and calculated as W is equals to F dot delta R, or F delta R cos theta, because we remove dot from that equation. F delta R cos 180 डिग्री. 180 डिग्री क्यों पुट किया हमने? क्योंकि अगेंस्ट द फील्ड मूव करवाया जा रहा है चार्ज को, टेस्ट चार्ज को, एंड W is equals to F delta R minus 1, because we know that cos 180 degree equals to minus 1. Now the work done will be W is equals to minus F delta R. By putting the value of A, which is EQ naught, because we know that E is equals to F upon Q naught. So we rearrange the formula and get W is equals to minus EQ naught delta R. Since electric potential difference between the plates can be calculated as delta V is equals to W upon Q naught, we know that electric potential को calculate करने के लिए हमारे पास formula होता है W upon Q naught, and W upon, by putting the value of W on that equation we get delta V is equals to minus E Q naught delta R over Q naught. Q naught will cancel Q naught and the remaining value will be delta V is equals to minus E delta R. If we have to calculate here the electric field value of electric field, so electric field is equals to E is equals to minus delta V upon delta R, and here the negative sign show the direction of movement of charge which is against the electric field. The delta V over delta R is its magnitude, which is always positive, but the negative sign always indicates the direction of the motion of the charge, which is opposite to the field. If it is in the direction of electric field, then the negative sign change into positive sign. Now the next topic is electron volt. इलेक्ट्रॉन वोल्ट नाम से जाहिर है हम बात करेंगे यहाँ इलेक्ट्रॉन की, और इलेक्ट्रॉन वोल्ट बेसिकली उस अमाउंट ऑफ एनर्जी या अमाउंट ऑफ वर्क डन का नाम है जो कोई भी इलेक्ट्रॉन किसी दो पॉइंट्स के दरमियान डिस्प्लेस करते वक्त अपने अंदर गेन करे या लॉस करे, और उस डिस्टेंस या डिस्प्लेसमेंट के दरमियान जो पोटेंशियल डिफरेंस हो वो 1 वोल्ट के बराबर हो. अकॉर्डिंग टू दिस we can write the definition of electron volt like this: the amount of energy acquired or lost by an electron when it is displaced across 2 points having potential difference 1 volt is called electron volt. Since as we know that W is equals to QV, work done बराबर होता है QV के, और यहाँ आपके पास क्योंकि चार्ज मूव कर रहा है बिटवीन टू प्लेट्स विच हैव द पोटेंशियल डिफरेंस 1 वोल्ट, so the moving charge have the kinetic energy, and this kinetic energy is equals to QV. Since Q is equals to 1.6 into 10 raised to the power minus 19 coulomb, because here we talk about the electron and the voltage between two plates is 1 volt, so 1 electron volt is equals to 1.6 into 10 raised to the power minus 19 into 1, and 1 electron volt is equals to 1.6 into 10 raised to the power minus 19 joule. This is the smaller unit of energy at atomic level. This is the end for today's lecture. If you have any query, then you can ask me on my WhatsApp or my personal mobile number. Thank you, students.